Introduction to Network Connectivity Center. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we will explore Google Cloud Platform's Network Connectivity Center, commonly abbreviated as NCC. This is a powerful hub-and-spoke connectivity management service that simplifies how you connect your various network resources across GCP and beyond. Network Connectivity Center serves as a centralized management point for all your network connectivity needs. Instead of creating complex point-to-point connections between every pair of networks you want to connect, NCC provides a hub that acts as a transit point. You connect your various networks to this hub as spokes, and the hub handles the routing between them automatically. Let me walk you through the architecture diagram. The central component is the NCC hub, which serves as the core transit point for all connectivity. From this hub, we have 4 different spoke types extending outward. The first spoke type is VPC spoke, which represents connections to virtual private cloud networks within GCP. The second spoke type is VPN spoke, which handles site-to-site VPN connections typically used to connect on-premises data centers or remote offices. The third spoke type is interconnect spoke, which manages dedicated cloud interconnect connections for high bandwidth, low latency connectivity to on-premises environments. The fourth spoke type is Router Appliance spoke, which allows third-party network virtual appliances, or NVAs, to participate in the NCC topology. Each of these spokes connects back to the NCC hub, creating a star topology. Traffic between any 2 spokes flows through the hub, which handles the route exchange and forwarding. This design dramatically simplifies network management because you only need to configure each spoke's connection to the hub, rather than creating direct connections between every pair of networks. The hub manages route exchange using Border Gateway Protocol, or BGP, ensuring that all connected networks can discover and reach each other dynamically as your network grows or changes. NCC prerequisites and initial setup. Before we can start configuring Network Connectivity Center, we need to ensure our environment is properly prepared. This involves enabling the required APIs and setting up the appropriate IAM permissions. Let me explain the gcloud commands shown on this slide. The first command is gcloud services enable network connectivity Google APIs.com. This command activates the Network Connectivity API in your GCP project. The gcloud services enable subcommand is used to enable a specific API or service. The parameter Network Connectivity Google APIs.com specifies the exact API identifier we want to enable, which is the core API required for all NCC operations. The second command enables compute.googleapis.com, which is the compute engine API. This API is required because NCC interacts with various compute resources like VPN gateways, interconnect attachments, and router appliances, all of which are managed through the compute engine API. The third command sets the default project using gcloud config set project followed by your project ID. The config set subcommand modifies the gcloud CLI configuration. The project property determines which GCP project will be used for subsequent commands. Replace your project ID with your actual project identifier. This saves you from having to specify the project flag on every subsequent command. The fourth command sets the default region using gcloud config set compute/region, followed by a region name like US Central 1. The compute/region property sets the default region for compute engine resources. This region will be used when creating regional resources if you do not explicitly specify a different region. Creating the NCC hub. The hub is the foundational component of Network Connectivity Center. All spokes connect to this central hub, which manages route exchange and data plane forwarding between connected networks. Let me walk you through the process of creating and verifying your NCC hub. The first command creates the hub using gcloud network connectivity hubs create followed by the hub name. In this example, we name our hub my NCC hub. The network connectivity hubs create subcommand initiates the creation of a new NCC hub resource. The positional argument my NCC hub specifies the name you want to assign to this hub. Hub names must be unique within your project and should be descriptive of their purpose. The description flag allows you to add a human-readable description to the hub. In our example, we use the description primary connectivity hub for hybrid network. This description helps team members understand the hub's purpose when viewing resources in the console or through CLI commands. While optional, descriptions are highly recommended for operational clarity. The labels flag enables you to attach key value pair labels to the hub resource. Labels are useful for organizing resources, tracking costs, and applying policies. In our example, we use labels environment equal operator production and team equal operator network ops. These labels can later be used to filter resources in queries or apply organization policies. The second command lists all hubs in your project using gcloud network connectivity hubs list. This command outputs a table showing all NCC hubs, their names, descriptions, and creation timestamps. Use this to verify your hub was created successfully. The third command provides detailed information about a specific hub using gcloud network connectivity hubs describe, followed by the hub name my NCC hub. The describe subcommand retrieves comprehensive details including the hub's unique URI, state, route exchange configuration, and associated spokes, creating VPC networks for spokes. Before we can attach VPC spokes to our NCC hub, we need to create the VPC networks themselves. Each VPC that will participate in the Network Connectivity Center topology needs to be properly configured with subnets and appropriate settings. The first command creates a VPC network using gcloud compute networks create, followed by the network name VPC spoke 1. The compute networks create subcommand creates a new virtual private cloud network. The positional argument VPC spoke 1 is the name we assign to this network. The subnet mode equal operator custom flag specifies that we want to manually create subnets rather than having GCP automatically create one subnet per region. Custom mode gives us precise control over IP addressing and subnet placement. The alternative value would be auto, which creates subnets automatically but uses predefined IP ranges that may conflict with your existing network design. The BGP routing mode equal global flag is critical for NCC. This setting determines how cloud routers in this VPC advertise routes. With global mode, a cloud router in any region will advertise routes to and from all regions where the VPC has subnets. This is essential for NCC because it ensures complete route visibility across your entire topology. The alternative regional mode would only advertise routes within the same region, which would break NCC's ability to provide full connectivity. The second command creates a subnet within our VPC using gcloud compute networks subnets create followed by subnet spoke 1. The network equal operator VPC spoke 1 flag specifies which VPC this subnet belongs to. The region equal operator US Central 1 flag places this subnet in the US Central 1 region, and the range equal operator 10.1.0.0/24 flag defines the IP address range for this subnet using CIDR notation. This gives us 254 usable IP addresses from 10.1.0.1 through 10.1.0.254. The diagram illustrates the VPC structure we are creating. VPC spoke 1 contains the subnet 10.1.0.0/24, which has a cloud route attached. This cloud route is what will ultimately connect to the NCC hub. Similarly, VPC spoke 2 has its own subnet 10.2.0.0/24 with its own cloud route, also connecting to the NCC hub. The hub facilitates route exchange between these two VPCs, enabling instances in one VPC to communicate with instances in the other. Creating cloud routers for VPC spokes. Cloud routers are essential components that enable dynamic routing through BGP. Each VPC that will be attached to Network Connectivity Center as a spoke requires a cloud router. The cloud router handles the BGP sessions that exchange routing information with the NCC hub. The first command creates a cloud router using gcloud compute routers create followed by the router name router spoke 1. The compute routers create subcommand initializes a new cloud router resource. The network equal operator VPC spoke 1 flag specifies which VPC network this router will be associated with. A cloud router must be attached to exactly one VPC network, and this association cannot be changed after creation. The region equal operator US Central 1 flag places the router in a specific region. Cloud routers are regional resources, meaning they operate within a single region. However, when the VPC has global routing mode enabled as we configured earlier, the router can advertise routes from all regions. The ASN equal operator 6500-1 flag sets the autonomous system number for this router. The ASN is a unique identifier used in BGP to identify your network. For private use within your organization, you should use ASNs from the private range of 64512 to 65534. Each cloud router that participates in NCC should have a unique ASN within your topology to ensure proper BGP route identification and prevent routing loops. The second command creates another router named router spoke 2 for our second VPC. Notice that we use ASN equal 65002 here, which is different from the first router's ASN of 65001. This ensures each router has a unique identity in the BGP topology. The third command, gcloud compute routers describe router spoke 1, displays detailed information about the router including its BGP configuration, advertised IP ranges, and status of any BGP peers. Attaching VPCs spokes to the hub. Now that we have our VPCs and cloud routers configured, we can attach them as spokes to our NCC hub. This is where the magic happens, as the spoke attachment establishes the data plane connectivity and initiates BGP route exchange. The command to create a VPC spoke is gcloud network connectivity spokes link VPC network create followed by the spoke name spoke VPC1. The network connectivity spokes link VPC network create subcommand specifically creates a spoke of type link VPC network, which is used for connecting VPC networks. The flag hub equal my NCC hub specifies which NCC hub this spoke will attach to. You can only attach a spoke to one hub, and this association is permanent unless you delete and recreate the spoke. The VPC network equal VPC spoke 1 flag identifies the VPC network that this spoke represents. The spoke creates a logical connection between this VPC and the hub. The region global flag indicates that this is a global spoke. VPC spokes in NCC are always global because VPC networks themselves are global resources that span all regions. This is different from other spoke types like VPN spokes, which are regional. The second command creates another spoke named spoke VPC-2 for our second VPC network VPC-spoke-2. Both spokes connect to the same hub my-NCC-hub, enabling connectivity between the two VPCs. The third command lists all spokes attached to a specific hub using gcloud network connectivity spokes list with the hub equal my NCC hub filter. This displays information about each spoke including its name, type, state, and the resource it connects. Looking at the data flow diagram, VPC spoke 1 with CIDR 10.1.0.0/24 sends its routes to the NCC hub. The hub processes these routes through route exchange and then advertises them to VPC spoke 2. Similarly, VPC Spoke 2 with CIDR 10.2.0.0/24 sends its routes to the hub, which advertises them to VPC Spoke 1. This bidirectional route exchange enables instances in either VPC to reach instances in the other VPC by routing through the NCC hub's data plane. Setting up Cloud VPN for hybrid connectivity. Cloud VPN allows you to extend your network connectivity center topology to include on-premises networks or other cloud environments. By creating VPN spokes, you can bring external networks into the NCC hub, enabling seamless routing between your GCP VPCs and external locations. The first command creates an HA VPN gateway using gcloud compute VPN gateways create followed by VPN-GW-on-prem. The compute VPN gateways create subcommand creates a high availability VPN gateway, which provides 99.99% availability through redundant tunnels. The network VPC Spoke 1 flag attaches this VPN gateway to our existing VPC. All VPN tunnels created on this gateway will have their traffic routed through this VPC. The region US Central 1 flag places the gateway in a specific region. VPN gateways are regional resources, and all tunnels on this gateway will terminate in this region. The second command creates an external VPN gateway using gcloud compute external VPN gateways create followed by external peer GW. This resource represents your on-premises VPN device or peer VPN gateway. The interfaces flag specifies the external IP addresses of your peer device. In this example, we configure two interfaces with addresses 203.0.113.1 and 203.0.113.2 for redundancy. Your actual values will be the public IP addresses of your on-premises VPN appliances. The third command creates the VPN tunnels using gcloud compute VPN tunnels create. The peer external gateway operator external peer GW flag specifies which external gateway this tunnel connects to. The peer external gateway interface operator 0 flag selects which interface on the external gateway to use, with 0 being the first interface. The shared secret flag provides the pre-shared key for IPsec authentication, and you should replace your PSK with a strong, randomly generated secret. The router operator router Spoke 1 flag associates this tunnel with a cloud router for BGP-based dynamic routing. The VPN gateway operator VPN-GW on-prem flag specifies which HA VPN gateway this tunnel belongs to. The interface operator 0 flag selects which interface on the HA VPN gateway to use. The diagram shows the VPN topology. The on-premises network connects through the Internet via IPsec tunnel to the high-availability VPN gateway. This gateway connects to the cloud router, which in turn connects to the NCC hub. From the hub, routes are distributed to both VPC Spoke 1 and VPC Spoke 2, enabling on-premises resources to reach any VPC in your NCC topology. Configuring BGP sessions for VPNs. After creating VPN tunnels, we need to configure BGP sessions to enable dynamic route exchange between your cloud router and on-premises router. BGP allows your networks to automatically discover and adapt to topology changes. The first command adds a border gateway protocol interface to the cloud router using gcloud compute routers add interface with router Spoke 1. The add interface sub-command creates a new interface on the router for border gateway protocol peering. The interface name operator BGP interface 0 flag gives this interface a name for reference in subsequent commands. The VPN tunnel operator tunnel 0 flag associates this interface with a specific VPN tunnel. The IP address operator 169.254.0.1 flag sets the cloud router's IP address for this BGP session. This address must be from the linked local range 169.254.0.0/16 and must match the peer IP configured on your on-premises router. The masked linked equal operator 30 flag creates a /30 subnet, which provides exactly two usable IP addresses, perfect for a point-to-point BGP link. The second command creates the BGP peer configuration using gcloud compute routers add BGP peer. The peer name equal operator peer on-prem O-0 flag names this BGP peer relationship. The peer ASN equal operator 65100 flag specifies the ASN of your on-premises router, which must be different from your cloud router's ASN to establish an eBGP session. The interface equal operator BGP interface -0 flag associates this peer with the interface we created earlier. The peer IP address equal operator 169.254.0.2 flag is the IP address of your on-premises router's BGP interface, which must be in the same /30 CIDR subnet as the cloud router's interface. The third command updates the router configuration using gcloud compute routers update. The advertisement mode equal operator custom flag switches from default route advertisement to custom mode, giving you control over which routes are advertised. The set advertisement ranges equal operator 10.1.0.0/24. 10.2.0.0/24 flag explicitly defines which CIDR ranges to advertise to your on-premises network. This ensures your on-premises routers know how to read both VPC's subnets, creating VPN spokes in NCC. After establishing VPN tunnels with BGP, we need to attach them as spokes to our Network Connectivity Center hub. This integration allows routes learned through VPN to be distributed to all other spokes in the topology. The first command creates a VPN spoke using gcloud network connectivity spokes link VPN tunnels create followed by the spoke name spoke VPN on-prem. The link VPN tunnels create sub-command specifically creates a spoke for VPN tunnel resources. The hub equal operator my NCC hub flag specifies which NCC hub this spoke will connect to. This is the same hub we created earlier and attached our VPC's spokes to. The VPN tunnels equal operator tunnel-0, tunnel-1 flag lists the VPN tunnels to include in this spoke. We specify both tunnels for redundancy, ensuring the spoke remains functional even if one tunnel fails. These tunnel names must match the tunnels you created in the previous steps. The region equal operator US Central 1 flag specifies the region where these VPN tunnels exist. Unlike VPC's spokes which are global, VPN spokes are regional because VPN tunnels themselves are regional resources. The second command describes the spoke to verify its configuration using gcloud network connectivity spokes describe. The output shows the spoke's state, which should be active, along with the URIs of the attached tunnels and the hub it connects to. The third command verifies route propagation using gcloud network connectivity hubs list routing table. This powerful command displays all routes known to the NCC hub, including which spoke originated each route and which spokes the route has been propagated to. This is essential for troubleshooting connectivity issues. The diagram shows the complete NCC topology with the VPN spoke integrated. The NCC hub sits at the center, connected to VPC spoke 1 with CIDR 10.1.0.0/24 and VPC spoke 2 with CIDR 10.2.0.0/24. The newly created VPN spoke connects through the VPN gateway to the on-premises network with CIDR 192.168.0.0/16. Routes flow bidirectionally, with the hub ensuring that on-premises routes reach the VPCs and VPC routes reach the on-premises network. Cloud Interconnect Integration Overview. Cloud Interconnect provides dedicated, high-bandwidth connectivity between your on-premises network and GCP. When integrated with Network Connectivity Center, Interconnect connections can share routes with all other spokes, creating a unified hybrid network topology. The first command creates a VLAN attachment for Dedicated Interconnect using gcloud Compute Interconnect's attachments dedicated create. The positional argument attachment on-prem one names this attachment. The interconnect equal operator my interconnect flag specifies which interconnect connection this attachment uses. This must be an existing dedicated interconnect that has been provisioned and is in active state. Provisioning a dedicated interconnect requires working with a colocation provider and typically takes several weeks. The router equal operator router spoke 1 flag associates this attachment with a cloud router for BGP peering. The region equal operator US Central 1 flag places the attachment in the same region as the router. The VLAN equal operator 100 flag specifies the 802.1x VLAN ID for this attachment. Your on-premises router must be configured to use the same VLAN ID. The bandwidth equal BPS_1G flag sets the maximum bandwidth for this attachment. Valid values include BPS_50M, BPS_100M, BPS_200M, BPS_300M, BPS_400M. The second command creates an interconnect spoke using gcloud network connectivity spokes linked interconnect attachments create. The hub equal my NCC hub flag connects this spoke to our hub. The interconnect attachments equal attachment on-prem 1 flag specifies which VLAN attachment to include. You can specify multiple attachments separated by commas for redundancy. The diagram illustrates the interconnect architecture. The on-premises router connects through a physical interconnect link to the colocation facility. From there, the connection reaches the Google Edge, which connects to the VLAN attachment. The attachment connects to the cloud router, which interfaces with the NCC hub. The hub then distributes routes to VPC Spoke 1 and VPC Spoke 2, providing high-performance dedicated connectivity from on-premises to all your GCP VPCs. Partner Interconnect Configuration. Partner Interconnect provides an alternative to Dedicated Interconnect when you cannot meet the colocation requirements or need smaller bandwidth allocations. With Partner Interconnect, you work with a supported service provider who has already established dedicated interconnect connections to Google. The first command creates a Partner Interconnect VLAN attachment using gcloud Compute Interconnect's attachments partner create. The positional argument partner attachment 1 names this attachment resource. The router equal operator router spoke 1 flag associates this attachment with a Google Cloud router that will handle BGP sessions. The router must already exist in the specified region. The region equals US Central 1 flag specifies where to create this attachment. You should choose a region where your service provider has presence and that is geographically close to your on-premises location. The Edge Availability Domain equal operator availability domain 1 flag specifies the edge availability domain for redundancy. Google's Edge network has multiple availability domains per metro area. For high availability, you should create 2 attachments in different availability domains. Valid values are availability domain 1 and availability domain 2. After running this command, GCP generates a pairing key that you must provide to your service provider. The second command retrieves the attachment details including this pairing key using gcloud Compute Interconnect's attachments describe. The output contains a pairing key field that looks like a long alphanumeric string. Share this key with your provider so they can complete the connection on their end. The third command activates the attachment after your provider has configured their side using gcloud Compute Interconnect's attachments partner update with the admin enabled flag. Until you run this command, the attachment remains in pending partner state and cannot pass traffic. Router Appliance Spoke Configuration. Router Appliance is an NCC feature that allows third-party network virtual appliances running on Compute Engine to participate in your NCC topology. This is useful when you need advanced routing features, SD-WAN integration, or want to use a specific vendor's networking solution within your GCP environment. The first command creates a compute engine instance that will serve as the router appliance using gcloud compute instances create. The instance name is NVIA-router-1, standing for Network Virtual Appliance. The zone equals US Central 1-A flag specifies the zone for this instance. Choose a zone in the same region as your other NCC resources for optimal latency. The machine type equal operator N2 standard 4 flag sets the instance size. Network virtual appliances typically need sufficient CPU and memory for packet processing. The N2 standard 4 provides 4 vCPUs and 16 GB of memory, suitable for moderate traffic volumes. The image family and image project flags specify the boot disk image. In this example, we use a Debian image, but in practice, you would use your NVIA vendor's marketplace image or a custom image with their software installed. The CAN IP forward flag is critical. It enables IP forwarding on this instance, allowing it to route packets between networks. Without this flag, the instance would drop packets not destined for its own IP addresses. The network interface flag configures the instance's network connections. The subnet parameter attaches the instance to your spoke subnet, and private network IP assigns a specific internal IP address. For NVAs, you typically want predictable IP addresses for BGP peering configuration. The second command creates a router appliance spoke instance resource using gcloud compute routers at interface on a cloud router. This configures the cloud router to peer with your NVA. The interface name gives this peering interface a name, and redundant interface specifies a backup interface for high availability. Looking at the diagram, the NVIA instance runs within VPC Spoke 1 and establishes a BGP peering relationship with the cloud route. The cloud route connects to the NCC hub, which then distributes routes to VPC Spoke 2 and VPN Spoke. This architecture allows the NVA to influence routing decisions and apply network policies to traffic flowing through the hub. Creating router appliance spokes. After setting up the NVIA instance and configuring BGP peering with the cloud router, we need to register the router appliance as a spoke in Network Connectivity Center. This integration allows routes from the NVA to be distributed to all other spokes. The first command creates the router appliance spoke using gcloud network connectivity spokes linked router appliance instances create. The spoke name spoke NVIA-1 identifies this spoke in the NCC topology. The hub equal my NCC hub flag connects this spoke to our existing NCC hub, enabling route exchange with all other attached spokes. The router appliance instances flag specifies the NVA instances to include in this spoke. The format is instance equal operator INSTANCE underscore URI, IP equal operator IP underscore ADDRESS. The instance parameter takes the full URI of your compute engine instance, which follows the pattern project/zones/instances/INSTANCE underscore NAME. The IP parameter specifies which IP address on the instance should be used for routing. If your NVA has multiple network interfaces, specify the IP of the interface participating in NCC. The region equal US Central 1 flag indicates the region where the router appliance instances are located. All instances in a single router appliance spoke must be in the same region. The site-to-site data transfer flag is an important option that enables data transfer between spokes through this router appliance. When enabled, traffic can flow from one spoke through the NVA to another spoke, allowing the NVA to inspect or modify inter-spoke traffic. The second command verifies the spoke creation and status using gcloud network connectivity spokes describe. Check that the state shows active and the router appliance instances are correctly listed. The third command lists all spokes attached to the hub, providing an overview of your complete network connectivity controller topology. The diagram illustrates the traffic flow through the router appliance. VPC Spoke 1 sends traffic to the NBA Router Appliance spoke, which can apply traffic inspection, security policies, or routing manipulation. The traffic then passes to the NCC hub, which forwards it to VPC Spoke 2. Return traffic follows the reverse path, ensuring the NBA can maintain connection state and apply symmetric policies. Site-to-site data transfer. Site-to-site data transfer is a powerful NCC feature that enables traffic to flow directly between spokes through the Google Backbone network. This is particularly useful for connecting branch offices, data centers, or cloud regions without requiring traffic to traverse your own network infrastructure. The first command enables site-to-site data transfer on a VPN spoke using gcloud network connectivity spokes update. The site-to-site data transfer flag activates this feature for the specified spoke. When site-to-site data transfer is enabled on a spoke, that spoke can exchange traffic directly with other spokes that also have this feature enabled. Traffic flows through Google's private backbone network, providing low latency and high bandwidth without traversing the public internet. The second command enables the same feature on another VPN spoke. For site-to-site data transfer to work between two locations, both spokes must have this feature enabled. The third command configures export and import filters on the hub using gcloud network connectivity hubs update. The export filters flag controls which routes are advertised to spokes, while import filters controls which routes are accepted from spokes. These filters use prefix lists to include or exclude specific site or ranges from route exchange. The diagram shows a typical site-to-site data transfer scenario. Branch Office 1 connects through a VPN gateway to VPN Spoke 1, while Branch Office 2 connects through another VPN gateway to VPN Spoke 2. Both spokes connect to the NCC hub. The key element is the Google backbone connecting the two VPN spokes directly. When an employee at Branch Office 1 needs to access a resource at Branch Office 2, traffic flows through the VPN to the first spoke, across the Google backbone to the second spoke, and down the VPN to Branch Office 2. This avoids routing traffic back through a central data center. Route advertisement policies. Route advertisement policies give you fine-grained control over which routes are exchanged between spokes in your NCC topology. This is essential for implementing network segmentation, preventing route leaks, and optimizing traffic flow. The first command creates a route policy using gcloud network connectivity hubs route tables create. The positional argument custom route table names this route table. The hub my NCC hub flag associates this route table with our NCC hub. A hub can have multiple route tables, each with different policies applied to different spokes. The description flag provides a human-readable explanation of the route table's purpose. The second command adds a route entry to the custom route table using gcloud network connectivity hubs route tables routes create. The route name is route to VPC2. The destination range equals 10.2.0.0/24 flag specifies which traffic this route handles. The spoke equals spoke VPC2 flag indicates that traffic matching this destination should be sent to the VPC2 spoke. The priority equals 100 flag sets the route precedence, with lower numbers having higher priority. The third command applies the route table to a specific spoke using gcloud network connectivity spokes update. The route table flag associates our custom route table with spoke VPC1. This means VPC1 will use our custom routing rules instead of the default route table. The diagram illustrates how route policies work within NCC. The NCC hub contains a policy engine that processes routes according to configured rules. The default route table provides baseline routing that all spokes use unless overridden. The custom route table contains specific rules for particular use cases. VPC Spoke 1 uses the custom policy, meaning it receives filtered or modified routes, while VPC Spoke 2 uses the default policy with full route visibility. This architecture enables scenarios like restricting which networks certain VPCs can reach. Configuring firewall rules for NCC traffic. Firewall rules are essential for securing traffic that flows through your NCC topology. While NCC handles routing between spokes, you still need to configure VPC firewall rules to allow or deny specific traffic patterns. The first command creates a firewall rule to allow traffic between NCC-connected VPCs using gcloud compute firewall rules create. The rule name is allow NCC internal. The network equal operator VPC-spoke-1 flag specifies which VPC this rule applies to. You need to create similar rules in each VPC that participates in your NCC topology. The direction equal operator ingress flag indicates this rule applies to incoming traffic. For bidirectional communication, you may also need egress routes depending on your security requirements. The action equal operator allow flag permits traffic matching this rule. The alternative is deny for blocking traffic. The rules equal operator all flag allows all protocols and ports. In production, you should restrict this to specific protocols like TCP:22, TCP:443, ICMP for better security. The source ranges equal operator quad 0/8 flag defines which source IP addresses can send traffic. This CIDR block covers all private IP ranges used by your VPCs and on-premises networks. Adjust this based on your actual IP addressing scheme. The priority equal operator 1000 flag sets the rule evaluation order. Lower numbers are evaluated first. Default rules have priority 65534, so 1000 ensures our rule takes precedence. The second command creates a similar route for the second VPC. Each VPC needs its own firewall rules as they are VPC-specific resources. The third command lists all firewall rules in a specific network using gcloud compute firewall rules list with the filter flag. The diagram shows the firewall rule evaluation flow. Traffic enters from the source network through NCC to the VPC. It first hits the allow NCC traffic rule, which permits inter-spoke communication. Next, any specific application rules are evaluated for service-specific policies. Finally, the implicit deny blocks any traffic not explicitly allowed. This layered approach ensures only authorized traffic flows between your connected networks. Monitoring NCC with cloud operations. Effective monitoring is crucial for maintaining a healthy NCC deployment. Google Cloud provides several tools to monitor connectivity status, traffic metrics, and route propagation across your topology. The first command retrieves the status of all spokes in your hub using gcloud network connectivity spokes list with additional formatting. The format flag customizes the output to show the spoke name, type, current state, and the resource it connects. This gives you a quick health check of your entire topology. The second command examines the hub's routing table using gcloud network connectivity hubs list routing table. This displays all routes known to the hub, showing the destination CIDR, next hop spoke, priority, and route type. Use this to verify that routes from all spokes are being properly exchanged. The third command retrieves detailed metrics using gcloud monitoring metrics descriptors list, filtered to network connectivity metrics. This shows available metrics like bytes sent and received, packet counts, and dropped packets for NCC resources. The fourth command creates a log sync for NCC-related events using gcloud logging syncs create. The log filter flag captures events related to network connectivity resources. Directing these to a BigQuery dataset enables historical analysis and alerting on connectivity changes. The diagram shows the monitoring architecture. The NCC hub generates data that flows into three monitoring systems. Google Cloud Monitoring receives metrics like throughput, latency, and error rates, which you can visualize in dashboards and use for alerting. Google Cloud Logging captures events such as spoke state changes, route updates, and configuration modifications. Network Intelligence Center provides topology visualization and connectivity tests that help troubleshoot issues across your hybrid network. Troubleshooting NCC connectivity. When connectivity issues arise in your NCC topology, a systematic troubleshooting approach helps identify and resolve problems quickly. Let me walk you through essential diagnostic commands and common issues. The first command runs a connectivity test using gcloud Network Management Connectivity Tests Create. This powerful diagnostic tool tests reachability between two endpoints across your network. The source instance flag specifies the source virtual machine for the test, using the format project/project/zones/zone/instances/instance. The destination IP address flag specifies the target IP to test connectivity to. The test analyzes the path and reports any configuration issues that would block traffic. The second command retrieves the test results using gcloud Network Management Connectivity Tests Describe. The output shows each hop in the path, what firewall rules were evaluated, and whether the packet would be delivered, dropped, or have an ambiguous result due to configuration issues. The third command checks BGP session status on a cloud router using gcloud Compute Routers Get Status. This displays the state of all BGP peers, showing whether sessions are established, the number of routes learned and advertised, and any error messages. A healthy BGP session shows state as established with non-zero route counts. The fourth command retrieves VPN tunnel status using gcloud Compute VPN Tunnels Describe. Key fields to check include status, which should be established, and detailed status, which provides information about IKE negotiation state and any errors. Multi-region NCC topology. Network Connectivity Center supports multi-region deployments, allowing you to build globally distributed network architectures. The NCC hub is a global resource, so spokes from any region can connect to the same hub and exchange routes. The first command creates a subnet in a different region, Asia East 1, within our existing VPC using gcloud Compute Networks subnets create. This demonstrates how a single VPC can span multiple regions while participating in NCC. The second command creates a cloud router in the Asia region using gcloud Compute Routers Create. Notice we use -ASN equal operator 65003, which is a unique ASN different from our other routers. This router will handle BGP for resources in the Asia region. The third command creates another HA VPN gateway in the Asia region using gcloud Compute VPN Gateways Create. This gateway enables VPN connectivity to on-premises or partner locations in Asia. The fourth command creates a VPN spoke for the Asia region using gcloud Network Connectivity Spokes Link VPN Tunnels Create. The key point is that we connect this Asia region spoke to the same hub, my NCC hub, that our US region resources use. The hub handles cross-region route exchange automatically. The diagram shows a multi-region NCC topology. The global NCC hub sits at the center, connecting resources across regions. In US Central 1, we have VPC spoke US and VPN spoke US handling North American connectivity. In Asia East 1, we have VPC spoke Asia and VPN spoke Asia for Asian connectivity. In Europe West 1, VPC spoke EU and Interconnect spoke EU handle European connectivity. All regions connect to the single global hub, which orchestrates route exchange so that any spoke can reach any other spoke regardless of region. Traffic between regions flows through Google's high-performance global backbone network. NCC Best Practices and Summary. As we conclude this presentation on configuring GCP Network Connectivity Center with gcloud commands, let me share some best practices and summarize the key concepts we have covered. The first command shows how to export your NCC configuration using gcloud Network Connectivity Hubs described with format =YAML output redirected to a file. Maintaining infrastructure as code through exported configurations and version-controlled scripts ensures you can recreate your topology if needed. The second command demonstrates cleanup by deleting a spoke using gcloud network connectivity spokes delete. When removing spokes, delete them before deleting the underlying resources like VPNs or interconnects to maintain proper dependency ordering. The third command deletes the hub using gcloud network connectivity hubs delete. You must remove all spokes before deleting a hub, as a hub with attached spokes cannot be deleted. For IP address planning, always use non-overlapping CIDR ranges across all connected networks. Network Connectivity Center cannot route between networks with overlapping address spaces. Document your IP allocation scheme and reserve space for future growth. For high availability, deploy redundant resources at every layer. Use multiple VPN tunnels, multiple interconnect attachments in different edge availability domains, and multiple Router Appliance instances. Enable site-to-site data transfer for resilient spoke-to-spoke connectivity. For security, implement defense in depth with VPC firewall rules, hierarchical firewall policies, and network segmentation using route policies. Regularly audit your NCC configuration and monitor for unauthorized changes. The diagram summarizes the complete NCC architecture we have built. Thank you for your attendance. Please consider subscribing to the channel and liking this video.